Okay, let's go over, what is this, test 4. First question gave you this reaction, and you had to identify the Bronsted-Lowry acid and the Bronsted-Lowry base. So first of all, we can see that these two compounds are connected, and likewise the water and the hydroxide are connected. Which one is the acid? Well, it's the water because it starts off as H2O and ends up hydroxide. And Bronsted-Lowry acids donate hydrogens. Since water is the acid, that means that the hydroxide is the conjugate base. And then it goes to reason that if water is the acid, that the other one must be the base. And you can see that it is the Bronsted-Lowry base because on the product side, it has accepted the hydrogen. So that means this is the conjugate acid. All right, number 2. Number 2 is a titration problem. And so what we have is 10 milliliters of 0.250 molar acetic acid. And we are titrating that with 0.250 molar sodium hydroxide. So what we've got is a weak acid and a strong base. Since it's a weak acid, we will need the Ka of the acid, which was on your Ka table. And it's 1.8 times 10 to the minus 5. A asks, what's the initial pH of the acid? And I'm going to work this without setting up an ice table because we did enough of these weak acid ones that y'all, I think you saw that, hey, we don't need an ice table. It's the same every time. And so what we do is we take the Ka, we set it equal to x squared divided by the initial concentration of the acid minus x. And remember, we would always say x is really small. Let me draw a line here to separate me working the problem from the information. We solve for x, and that's 2.12 times 10 to the minus 3 molar. That is the concentration of the hydrogen. We know that because we used the Ka. So x must be the concentration of the hydrogen. The negative log of that is the pH, which is 2.67. Okay. B part asks for the pH after we've added 7.5 mils. So this number would be 7.5. I'm not going to leave that there because it changes each time. So I'm going to set up an ice table for that where we take acetic acid, which is CH3COOH, plus the sodium hydroxide, and that's going to make sodium acetate and water. Initially, we start with 0.25 molar acetic acid and 10 mils of it, which is 0.01 liters. If we multiply these together, that gives us the moles, 2.50 times 10 to the minus 3 moles. And then we're likewise starting with 0.250 molar sodium hydroxide. But in B part, as I said, it gave you 7.5 mils of the strong base, which is 0.00750 liters. And we would multiply those together, and that means I'm starting with 1.875 times 10 to the minus 3 moles of strong base. So that's my initial moles. Change, this is a limiting reactant problem. So since the sodium hydroxide is the smaller number, it means I'm going to use all of it. And I won't have any sodium hydroxide left. And because of that change line, remember, it follows the stoichiometry of the reaction. So likewise, I'm going to use 1.875 times 10 to the minus 3 moles of acetic acid, and I'm going to make 1.875 times 10 to the minus 3 moles of the sodium acetate. Of course, the water is not going to matter because it's a liquid, and liquids do not show up in the equilibrium expressions. So then I subtract here, and at equilibrium I have 6.25 times 10 to the minus 4 moles of acetic acid and 1.875 times 10 to the minus 3 moles of sodium acetate. Okay, What's going on here is we have weak acid, acetic acid, and we have acetate, its conjugate base. And so if you have weak acid and its conjugate base, you have a buffer, which means you need to use that Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. We used the Ka earlier, 1.8 times 10 to the minus 5. So the pKa is the negative log of the Ka. The pKa is 4.74 plus the log. And I'm just going to use these mole amounts instead of the concentration. You could divide by the total volume of 17.5 milliliters converted to liters. But since this expression is a ratio of base to acid, then converting that to molarity is not going to change the math of it. Okay, so Henderson-Hasselbalch equation gives us for B a pH is 5.22. Okay, then C part says calculate the pH at the equivalence point. The equivalence point means I have equal moles of acid and base. So I'm going to copy the ice table from the first part. If I start with equal moles of acid and base, then that means I have 2.5 times 10 to the minus 3 moles of acetic acid. I've got 2.5 times 10 to the minus 3 moles of the base. That means I use all of it. When it's all said and done, I don't have any acid or any base left over. What I have is salt. 2.50 times 10 to the minus 3 moles of salt. Okay, that says moles. The concentration of the salt, and it's the sodium's not going to matter. The sodium's not going to affect the pH, but it's the acetate that is. The concentration of the salt is going to be 2.5 times 10 to the minus 3 moles divided by the total volume. So let me scroll back to our original information here. At the equivalence point, we always have 10 mils of acetic acid. At the equivalence point, we also have to have 10 mils of the strong base. That's what makes those moles be equal. So our total volume at this point, y'all see, is 20 milliliters. So I take this salt and I divide it by 0.020 liters. That means the concentration of the salt is 0.125 molar. Now, the Ka we used earlier was for acetic acid. So see, the Ka for acetic acid is 1.8 times 10 to the minus 5. But what we have here is the acetate, so we need the Kb. To calculate the Kb, you say Kw divided by the Ka. And so for Kb, it is 5.56 times 10 to the minus 10. Then, hopefully, I hope all that's familiar, but at this point, you combine this information and you say Kb, 5.56 times 10 to the minus 10, is equal to x squared divided by 0.125 minus x. We pretend it's really small. Solve for x. X is 8.34 times 10 to the minus 6. Now, since we used a Kb, remember, X is hydroxide ion concentration. So the negative log of the X is the POH, which is 5.08, and then 14 minus that is the pH, which is 8.92. And so in my mind, maybe in yours, maybe not, that was one of the hardest problems on the test, was specifically part C. Okay, number 3. You are titrating, again, 25 milliliters of 0.100 molar nitric acid with 0.100 molar KOH. you must first recognize this is a strong acid and a strong base. So what's the initial pH of a strong acid? That's what A asks for. Well, since it's a strong acid, the pH is the negative log of the hydrogen ion concentration, which is 0.1. Remember, strong acids completely ionize, so the pH is 1. And then in B part, it says what's the pH at the equivalence point. Well, what does that mean? Same thing as before. It means the moles of acid and moles of base are equal. It means that you had 25 milliliters of this. You didn't have to know that because y'all know that a strong acid and a strong base makes a neutral salt. Therefore, B, the pH at the equivalence point, is 7 because the salt's neutral. Okay, number 4. 4 says, calculate the initial pH of a buffer. All right, buffer, keyword. pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. And it says the buffer is 0.250 molar ammonia, which is NH3, and it's 0.350 molar ammonium chloride. Now look at those formulas. You can tell from the formula that this one's going to have to be the acid and this one's going to have to be the base. How can you tell? The acid has an extra hydrogen. Okay, in the formula, you need a pKa. Y'all know we covered it already here. pKa is the negative log of the Ka. Well, you can't find a Ka for ammonium, so you're going to have to look up the Kb for ammonia on your ice table. The Kb is 1.8 times 10 to the minus 5. It just so happens that the Kb for ammonia is the same Ka for acetic acid that we used earlier. That might be looking familiar to you. You're going to do again Kw divided by Kb to figure out what the Ka is. And the Ka is going to be 5.56 times 10 to the minus 10. The negative log of the Ka is the pKa, which is 9.26. And so we're ready to plug in. The pH is equal to 9.26 plus the log. The base is the 0.250 molar. The acid is the 0.350 molar. So the pH is 9.11. Okay. Then B part, I'm going to work that in magenta. It says calculate the pH of the same solution after you add 0.1 moles of strong base. 0.1 moles of strong base is going to increase the base by 0.1 and it's going to decrease the acid by 0.1 because you're adding to the base, but that acid is going to be used to neutralize it. And like we worked on in class on the problem on the test, I said assume the volume remains constant. So what that means is on B part, you can say that the pH is equal to the pKa, which is 9.26, plus the log of, you do the math, 0.25 plus 0.1 is 0.35, and then 0.35 minus 0.1 is 0.25. And so look, we started with a pH of 9.11. In B, we're adding base, so the pH should increase from that. And indeed, this calculation shows it goes up to 9.41. Okay, number 5 says, predict where the following solutions will be acidic or basic or neutral. And you are given, make sure mine is just like y'all's. Yeah. You are given ammonium chloride as the first one. Let's see, you're given sodium chloride. You're given bismuth 3 nitrate. These are not in formulas. They're in, it's written out word forms. And you're given cesium formate. Okay. Now, is it an acid, base, or neutral? Ammonium chloride, I don't know how y'all, how it makes sense in your head, but ammonium chloride's a salt. There's different ways to approach this. That salt could be formed by the combination of ammonia and hydrochloric acid. So I recognize, hey, that's a weak base and that's a strong acid. Therefore, this salt is acidic. Okay. Sodium chloride could be formed from sodium hydroxide and hydrochloric acid, which is a strong base and a strong acid. Therefore, that salt is neutral. Okay. Bismuth 3 nitrate could be formed from bismuth hydroxide and nitric acid, which is a strong acid. And bismuth 3 hydroxide is not a strong base, so it has to be a weak base. That means this salt is going to be acidic. And then cesium formate could be formed from cesium hydroxide and formic acid. The formula for formic acid was on your Ka table. But cesium hydroxide is a strong base. Formic acid is a weak acid. That means this salt would be basic. Okay, then you had to take that information, and in number 6, let's see, I should have left some space there. It says if you raise the pH, what's that going to do to solubility? Well, if a salt is acidic and you raise the pH, that means it's going to be more soluble. If a salt is neutral and you raise the pH, that means it's going to do nothing, because neutral salts aren't affected by pH. So in here, since the salt's acidic, if you raise the pH, it's going to make it more soluble. And then the flip of that, if the salt is already basic and you raise the pH, it's going to be less soluble. And so the way I told y'all that in class, once you identify the pH of the salt, if you need it to dissolve more, you've got to move away from the salt pH, right, to make it dissolve more. Okay, number 7. You were given the choice of H3PO4 and H3ASO4 and asked which one is a stronger acid. Well, clearly the difference in these is the phosphorus and the arsenic. It's based on electronegativity. Which one's more electronegative? It's the phosphorus. Therefore, H3PO4 is the stronger acid because phosphorus is more electronegative. That is going to pull the electrons away, and H3PO4 would more readily release the hydrogens. Then in number 7, I think, if I remember correctly, somebody tried to talk about size, like they looked at the periodic table and said phosphorus, arsenic. Arsenic is bigger, so therefore it's the stronger acid. Y'all, you only look at size when you're comparing, remember, just the hydrohalic acids. Like this. Increase size, increase acidity. So HI is strongest, then HBr, then HCl, then HF. But when you're looking at oxo acids, like these, it's H, oxygen, and something else. You're always looking at electronegativity. Okay? Number 8, calculate the solubility of iron 2 hydroxide. And I underlined solubility because you weren't supposed to calculate just the molar solubility. You needed the solubility, so you need grams per liter. You were given that the KSP is 1.6. I gave it to you. Yeah, times 10 to the minus 14. And y'all know that iron 2 hydroxide is this. So it's going to, I'm going to over-explain it here. It would ionize as iron ions and 2 hydroxide ions. So isn't that 1x and 2x? So that means that the KSP is equal to 4x cubed. Now I plug in. The KSP is 1.6 times 10 to the minus 14. I solve for x. You divide by 4 and you take the cube root of it. And x is 1.59 times 10 to the minus 5. That's molar solubility, which is moles per liter. But the question said, what's the solubility? That means you have to go from moles to grams. So you need the molar mass of iron 2 hydroxide, which is 89.87 grams per mole. And you get 1.43 times 10 to the minus 3 grams per liter. Number 9 gives you a solubility of 0.073 grams per liter and says calculate the KSP. Do y'all see that number 9's right? It's opposite. It starts you, like in number 8, it starts you here and asks you to go back to that. Just with a different, it's not with iron 2 hydroxide. It says KSP. It says the solubility of strontium fluoride. Strontium fluoride is SRF2. So I'm going to take the 0.073 grams per liters. I'm going to go from grams to moles. Molar mass is 125.62. So that gives me a molar solubility of 5.81, times 10 to the minus 4 molar. Since it's SRF2, do y'all see that the KSP is equal to 4x cubed? And that 5.81 times 10 to the minus 4, that's x. Cube it, multiply it by 4. KSP is 7.85 times 10 to the minus 10, which is unitless. Okay. Finally, number 10. Number 10 says we've got 4 milliliters of 0.100 molar copper 1 nitrate, which is CuNO3. And we're going to combine it with 125 milliliters of 0.00850 molar sodium bromide, which is NaBr. It does, I have the names on the test, but y'all know that will be the formula. And the question is, will CuBr precipitate? And you got to show your work. Okay. We need the KSP for CuBr. We look it up on the table. The KSP is 4.2 times 10 to the minus 8. We have to use the information in the problem to calculate a reaction quotient, Q. Remember, the reaction quotient is calculated exactly like the KSP. In other words, Q is going to be equal to the concentration of the copper times the concentration of the bromide. How do we figure out the concentration of the copper? Well, clearly it's coming from copper 1 nitrate. And so to figure out the concentration of the copper, we're going to say M1, 0.1 molar, V1, 4 milliliters, is equal to M2, which is what we're solving for, times V2. And the V2, guys, is 129 milliliters. So M1.1 times 4 divided by 129, and if both of your volumes are in milliliters, you can leave it that way. You don't have to convert to liters. Okay, and so that gives us that the concentration of the copper is 0.0031 molar. Then we have to figure out, well, what's the concentration of the bromide? Clearly it's coming from the sodium bromide, so we use, this is M1. This is V1, and then again, V2 is still 129 milliliters. And we solve, and we get that the concentration of the bromide ion is 0.00824 molar. Okay, multiply that together, and we get Q, which is 2.6 times 10 to the minus 5. Compare the KSP and the Q. Q is bigger. Since Q is bigger than the KSP, it means the reaction is going to move in reverse, which means, yes, a precipitate will form. Okay, so what reverse reaction are we talking about? We're talking about the KSP for CuBr. Okay, if you'll remember, or you can look at your KSP table, this is the KSP reaction. It's CuBr solid, makes copper and bromide. And see, if this reaction moves in reverse, it forms the precipitate, that's why the answer is yes. Okay, hope that helps, guys.